Ever pondered why the universe in all its grandeur appears flat and not curved? Our cosmic home, the universe, is a vast expanse of galaxies, stars, and the mysterious dark matter. Yet when we look into the deep recesses of space, the universe presents itself not as a curved expanse, but as a flat plane. It's a bit like standing in the middle of a gigantic desert. Look in any direction, and the horizon seems flat, stretching out to infinity. This is an intriguing enigma that has puzzled scientists for centuries. Why does the universe, with all its celestial bodies and complex phenomena, appear to be flat? Is it truly flat, or is this just an illusion? And if it is indeed flat, what does this mean for our understanding of the cosmos? These are the questions that we'll be exploring in this cosmic journey. To understand this flatness, we need to delve into the realm of cosmological geometry, the branch of science that studies the shape and structure of the universe. It's a bit like trying to determine the shape of a balloon by studying its surface. And just like the balloon, the universe also has a shape determined by its overall geometry. But the universe isn't a simple balloon. It's a complex system filled with countless galaxies, stars, and other celestial bodies, all of which contribute to its overall shape and structure. And yet, despite all this complexity, the universe appears to be flat. This is what scientists refer to as the Flatness Problem, a puzzle that has baffled cosmologists for decades. As we journey through this cosmic mystery, we'll explore various theories and concepts that attempt to explain the flatness of the universe. From the cosmic microwave background radiation to the concept of cosmic inflation, from the observation of distant galaxies to the enigmatic dark energy, each piece of the puzzle brings us closer to understanding the true nature of our universe. So join us as we embark on this exciting journey into the cosmos, delving into the mysteries of the universe's geometry, exploring the enigma of its flatness, and seeking answers to some of the most profound questions of our existence. Stay tuned as we unravel the mysteries of the cosmic flatness. Ancient cultures had their unique perceptions about the universe's shape. Let's embark on a journey through time to understand the evolution of our cosmic perspective. In the beginning, humans perceived the world around them as flat and finite. The heavens were imagined as a dome studded with stars encasing the flat Earth. The Greeks were among the first to challenge this view. The philosopher Pythagoras proposed the Earth was a sphere, and later, Aristotle provided physical and observational evidence supporting this. With the spherical Earth established, the concept of a curved universe began to take root. Fast forward to the Middle Ages, and we see the Ptolemaic model of the universe with Earth at its center. This geocentric model was widely accepted until the 16th century, when Copernicus introduced his heliocentric model, placing the Sun at the center of the universe. The 20th century brought a revolution in our understanding of the universe's shape. Albert Einstein's theory of general relativity introduced the idea of a universe that could be curved, flat, or even saddle-shaped, depending on its density. Around the same time, astronomer Edwin Hubble discovered that galaxies were moving away from us in every direction, suggesting that the universe was expanding. In the latter half of the 20th century, cosmologists proposed the theory of cosmic inflation. This theory posits that the universe underwent a rapid expansion shortly after the Big Bang, which could explain its large-scale uniformity and flatness. Today, our best measurements suggest that the universe is flat. However, this doesn't mean it's a two-dimensional plane. Instead, it means that if you and a friend were to set off in two rocket ships in parallel paths, you would remain parallel forever, never meeting or diverging. As we advanced, so did our understanding of the universe. The journey from flat Earth to flat universe is a testament to human curiosity and our relentless pursuit of knowledge. Yet, the universe holds many more secrets waiting to be unraveled. So let's keep exploring. The shape of the universe is tightly entwined with its geometry. When we talk about cosmic geometry, we are delving into the relationship between the universe's shape and the laws of physics that govern it. Now, you might be wondering, how can the universe have a shape? Isn't it infinite and boundless? Well, in cosmology, the shape of the universe doesn't refer to its outer boundary, but rather its overall structure and the patterns that emerge within it. The geometry of the universe is determined by mass, energy, and the rate of expansion. Together, these factors govern the curvature of space, the trajectories of galaxies, and the paths of light beams. In a flat universe, like the one we inhabit, the geometry is Euclidean. This means that parallel lines will never meet, and the angles in a triangle always add up to 180 degrees. It's the geometry we learn in school, but applied on a cosmic scale. But what if the universe wasn't flat? If there was enough mass and energy to slow down expansion, space could curve back on itself, creating a closed spherical universe. Conversely, if expansion was too fast for mass and energy to keep up, space would curve away from itself, resulting in an open, saddle-shaped universe. Yet all our observations point to a flat universe. The cosmic microwave background radiation, the oldest light in the universe, shows patterns consistent with flat geometry. The distribution of galaxies across the cosmos also aligns with a flat universe model. The geometry of the universe is not just about shapes and angles. It's about understanding the fundamental nature of the cosmos. It encompasses the past, present, and future of the universe, shedding light on the birth, evolution, and ultimate fate of everything that exists. The universe's geometry is indeed a tale of cosmic proportions. It's a story written in the language of physics and mathematics, waiting for us to decode its secrets and unravel the mysteries of the cosmos. The cosmic microwave background radiation, or CMB, is our window into the universe's past. This relic radiation dates back to a time only a few 100,000 years after the Big Bang, when the universe cooled enough for light to travel freely. The CMB is not just a historical record, though. It's a cosmic detective, its patterns and fluctuations offering crucial clues about cosmic geometry. Scientists study these patterns to determine the curvature of the universe. If the universe were curved, these patterns would appear distorted. But what we observe aligns remarkably well with the predictions for a flat universe. It's as though the universe is a humongous sheet of graph paper, with galaxies plotted along its grid lines. The cosmic microwave background radiation, then, is a bit like a cosmic whisper, carrying a message from the distant past. A message that tells us, in its subtle, statistical way, that our universe is flat. The CMB, like a cosmic whisper, reveals secrets about our universe. The flatness of the universe is more than just a fact, it's a cosmic puzzle. This puzzle isn't about whether the universe is flat, but rather why it is so. The universe's observed flatness is so precise, it's almost too good to be true, and this, dear folks, is what cosmologists call the Flatness Problem. Our universe, it seems, is finely tuned. If it had been even slightly more curved, matter would not have been able to coalesce into galaxies. A slight tweak in the other direction, and matter would disperse too quickly, leaving no chance for stars and galaxies to form. The universe appears to be just right. A Goldilocks universe, if you will, perfectly balanced for the existence of complex structures like galaxies, stars, and perhaps life itself. This precision is baffling. Why is our universe so perfectly flat? This question is what cosmologists refer to as the Flatness Problem. The Flatness Problem challenges us to look beyond the obvious. Enter cosmic inflation, the proposed solution to the Flatness Problem. This theory, put forth in the late 20th century, suggests that a fraction of a second after the Big Bang, the universe underwent a rapid expansion, growing exponentially in size. This sudden growth spurt, or inflation, stretched the fabric of the universe, smoothing out any initial curvature and resulting in the large-scale flatness we observe today. It's akin to blowing up a balloon. As the balloon inflates, its surface becomes increasingly flat to an ant crawling on it. Similarly, as our universe inflated, it became flatter on a cosmic scale. This inflationary period is believed to have ended after a tiny fraction of a second, but its impact was monumental. It set the stage for the formation of galaxies, stars, and ultimately us. Inflationary theory paints a fascinating picture of our early universe. It's like a cosmic detective story, where we're piecing together clues to understand our origins. The universe isn't static, it's constantly expanding. Imagine blowing up a balloon. As you pump in more air, The surface of the balloon stretches out. In much the same way, the universe is expanding, with galaxies moving away from each other in all directions. Now, this expansion isn't due to galaxies physically moving through space. Instead, it's the space itself that's stretching out. This concept of an expanding universe plays a huge role in our understanding of its overall geometry. The rate at which the universe expands influences whether it's flat, curved, open, or closed. If the universe is expanding at just the right rate, the geometry will appear flat. Too slow, and the universe would curve in on itself. Too fast, and it would curve outward. The universe's expansion is a testament to its dynamic nature. It's not static, but rather in a constant state of change and evolution. Dark energy, the elusive force behind the universe's accelerated expansion. This invisible energy, constituting around 70% of the universe, is believed to be the driving force that's pushing galaxies apart at an ever-increasing rate. But how does this relate to the geometry of the universe, you might ask? Well, the presence of dark energy affects the rate at which the universe expands, and this expansion rate directly influences the overall geometry of the cosmos. If the amount of dark energy were too low, the universe could curve in on itself, creating a closed universe. Conversely, too much dark energy could cause the universe to curve outward, forming an open universe. However, the current amount of dark energy appears to be just right, maintaining a delicate balance that keeps the universe flat. So, despite its elusive nature, dark energy plays a vital role in preserving the flatness of our universe. Dark energy, although mysterious, plays a critical role in shaping our universe. Measuring cosmic distances, a crucial step in understanding the universe. Now, you may wonder, how on earth do we measure the vast expanses of the cosmos? Well, astronomers have a few clever tricks up their sleeves. They use specific techniques like standard candles and redshift to gauge the distances of celestial bodies. Standard candles, such as certain types of supernovae, have a known brightness that enables us to calculate their distance. By observing how much their light has redshifted or shifted towards longer wavelengths, we can estimate how far the light has traveled. These measurements play a pivotal role in shaping our understanding of the universe's geometry. They provide us with a cosmic ruler, allowing us to map out the universe and determine its overall shape. And what do these measurements tell us? They consistently point towards a flat universe. Every measurement brings us closer to understanding the true nature of the universe. Observational evidence, our touchstone for understanding the universe. It's through this lens that we see the flatness of our universe. The patterns in the cosmic microwave background radiation, the large-scale uniformity, the rate of expansion, all these pieces of evidence point towards a flat universe. Let's consider the Planck satellite, which has provided us with the most precise measurements of the cosmic microwave background radiation. The patterns it observed align beautifully with a flat universe model. Similarly, studies of distant supernovae, our cosmic lighthouses, also suggest a flat universe. And then there's the large-scale structure of the universe. The way galaxies cluster and form vast cosmic webs also seems to fit best within a flat universe. So, from the cosmic microwave background to supernovae to the large-scale structure of the universe, all lines of observational evidence point towards flatness. Observations confirm the universe's flatness, but the quest for understanding continues. Our journey through the cosmos brings us back to where we started, pondering the flatness of the universe. We've delved into historical perspectives, wrestled with cosmic geometry, and explored the revelations of the cosmic microwave background radiation. From the perplexing flatness problem to the enlightening theory of cosmic inflation, we've journeyed through the expanding universe, encountering the mysteries of dark energy along the way. We've measured the vast expanse of the cosmos and peeked into the evidence that supports the universe's flatness. We've toyed with alternate geometries and delved into theoretical concepts from the realms of general relativity and quantum physics. And all along, we've been fascinated by the philosophical implications of a flat universe. The universe, in its grandeur and mystery, is a puzzle that continues to challenge our understanding. Its flatness, a concept that may seem simple at first, holds profound implications about the nature of reality and our place in the cosmos. The geometry of the universe isn't just about lines and angles. It's about the fabric of space and time, the energy that drives cosmic expansion, and the patterns of light left over from the universe's earliest moments. Even as we've explored these concepts, remember that our understanding is continually evolving. New discoveries, technologies, and theories may yet reshape our perception of the universe's geometry, its flatness, and its infinite expanse. We are part of an ongoing journey of discovery, a cosmic adventure that spans the depths of space and the frontiers of human knowledge. So continue to gaze at the stars, to question, to wonder. The universe invites us to explore, to learn, to grow. As we unravel its mysteries, we come to see ourselves not as separate observers, but as integral parts of this vast cosmic tapestry. Our understanding of the universe's flatness is just one thread in that tapestry, a thread that connects us to the cosmos and to each other. As we continue to explore, the universe continues to amaze, reminding us that we are but a small part of this grand cosmic tapestry.